Hi. If you're watching this video, hopefully you're looking to get a little bit of Regents review while the New York State Chemistry Regents still exists the way that it does. Just a quick introduction, some best practices before we get started. The number one most important thing you can have available is right here. It's a QR code that's going to point you to the New York State chemistry reference tables. It has all of the information that you will get when you take the test, and arguably a lot of the information you're going to need to take the test. Things otherwise you might want to have, some sort of a calculator handy. And if you need a paper copy or digital copy of the Regents, there will be a link below. It is suggested that you take a look at these questions before you watch this video. It might move a little bit fast for some people, but hopefully you find this helpful, and let's get started.
This is the January 2023 Regents, Part A, first half, 15 questions. Just a quick breakdown of the test in case you're not familiar. Part A really is a survey of the entire year. Questions will go roughly in the chronological order that you saw in class, depending on what your teacher did. There's a lot more concepts over calculation problems, definitions over execution. Everything's fair game. So as such, you might expect a little bit more periodic table or reference table use than you might see elsewhere, but when it comes up in the questions, I will try and highlight things here. So looking at the first question, we've got a history of the atom on our image on the slide. Look out for reference, but this is something that you should have in your head. The gold foil experiment, that was Rutherford in 1911. That's the center one on this picture, and I blew it up on the bottom here, so you can go ahead and read. Which one agrees with his conclusions of his experiment is that atoms are mostly empty space. Hard spheres are Dalton, different volumes and same volume don't really apply in this case. For question 2, this might be something you've committed to memory, but if you haven't, Table O does list information about each of the particles that you would see inside an atom or things that are involved in nuclear decay like alpha and beta particles. So you can look it up. The top number is the mass. So you're looking for two particles with the same top number, which would be the proton and the neutron, which is choice 4. Electrons, don't forget, have a mass that's way lower than a proton or a neutron. When talking about atoms emitting energy, especially when electrons are transitioning in levels, the first shell is the one that's closest to the nucleus, second, further away, and third, even further away. And as you get further away from the nucleus, the electron is overcoming the attraction to the positive nucleus, so the electrons that are further away have to have more energy than the ones that are closer. And the only way that motion occurs is through either absorbing or releasing energy. So we're looking for emit, which is the same thing as release, and that would be moving down. So from a higher number, a bigger number, to a smaller number, which the only question that does that is choice 4. If for some reason you forgot some piece of that, you can maybe in this case look at the answer choices, and the first 3 are all lower number to higher number. The fourth one is a higher number to a lower number. I can't promise that'll always work, but sometimes that does give you the right answer. For number 4, we're looking for a metal, a metalloid, and a noble gas. Metals are on the left side of your periodic table, nonmetals are on the right side of your periodic table, and the staircase between them, this diagonal stepping line, is the metalloids that you're expected to be familiar with. I've circled the 6 big ones. Astatine, polonium, tennessine, as we start to update the periodic table, might be, but a lot of these elements are radioactive, so we don't really worry about their chemical properties too much. So we're looking for one from the left side, which is most of the periodic table. I included the bottom 2 rows in place for an extended periodic table, and then the nonmetals being on the right, which would point us to, I believe, choice 2. Because rubidium and strontium are both metals. Yeah, I think that's the case. You could go through each one to check, but the only one that has one from the left, one from that staircase, and one from the right is choice 2. Which element has the lowest density at 298 K and 131 kilopascals? I've copied over a section from table S for you here. It got a little chopped off by the question. You can look at this question without going to table S, but table S does list the density of each element, and it is not necessarily at those temperature and pressure conditions, but as temperature and pressure fluctuate, density will fluctuate in a similar fashion. So if it's lowest at one condition, it's lowest at all conditions. So our 4 choices are nitrogen, oxygen, and fluorine up here, and argon down in the bottom. All you have to do is read the table. If we go over to the second to last column, we'll see that the lowest of the set is nitrogen here, so that's our answer. If you didn't want to look it up on table S, a different choice you could make would be to say all gases, if you've got the same sample, the same volume at the same temperature and the same pressure, they all have the same number of particles present. And so looking at these particles, you could go and try and figure out the masses of the particles. Remember that nitrogen, oxygen, fluorine are diatomic. So you'd have 28, 32, 19, and 19 is 38. And then argon is 40. So again, we still have the lowest mass in a given volume if you want to go more of a conceptual route with it. Question 6 shows up about every Regents or so, maybe every other, and it's this question about where properties and structure meet. Property and structure are a direct relationship, so I included pictures here of what graphite and diamond look like, but you don't really need that to answer the question. If you've got 2 different forms of solid carbon and they have different names, then you know that they have different properties, and they can't have different properties unless they have different crystal structures. And you can see from the images they have different crystal structures, but I don't expect you to commit these to memory. So the answer here is different, which is choice 3. Question 7, similar chemical properties come about because of the valence electrons present in the atoms in their ground state. So that's the last number as you're looking at the electron configuration. The chemical properties are more dependent on the number of valence electrons, even if it's in a different energy level. And so in this case, if we're looking at sodium, which is Na, you can confirm that on table S if you don't know that. We're looking for one that's in the same column, the same group. So that's not magnesium, and it's not oxygen, and it's not phosphorus. That is rubidium. That's the one 2 under, but it's in the same columns. They both have that 1 valence electron. This is one of the vocab questions you're going to see in part A. Which substance contains elements chemically combined in a fixed proportion? That is a definition. That is code for compound. And that translates to 2 or more elements. If you don't have all the elements of the periodic table memorized, that's okay. You're not expected to. But you might have to then spend some time looking at table S, which gives you properties of selected elements. So if it's on table S, it's not a compound. That's how we're going to find an answer to this question. Strontium, silicon, and manganese are all on your table, so none of those are the answer, leaving choice 2, which is methane. If you do remember your organic chemistry, methane should jump out at you as a hydrocarbon, which is a compound of carbon and hydrogen. Again, it's a compound. For number 9, that's an interesting question how they go about it. They give you a lot of information, and if you'll notice, a lot of the information is the same between the 2 samples that you have of potassium nitrate and silver chloride. They're solids, they're 50 grams, and they're at STP. So since they're both solids, you know the phase is the same, and we're talking about differentiating. Since you know that they're both 50 grams, they have the same mass, and since they're both at STP, which is standard temperature and pressure, they have the same temperature, and really the only thing that's left there is solubility. That's more of a decipher information in the question. Do you know what all these words and all these terms mean? For question 10, we're looking at the type of bonding that occurs when you're sharing electrons. So bonding, shared, that for like when you put that all together, you should say, sharing is covalent. And that will start to narrow down your choices because ionic should not be an answer choice. Hydrogen bonding is not a bond. It's an intermolecular force, meaning that's a force felt in between molecules, and that's not what we're talking about. We're talking about electrons shared between 2 atoms in a particle, not between 2 particles. So now we've narrowed this down to choices 1 or 2. Is it polar or is it nonpolar? I have some images here to help jog your memory in case this is something you've seen and forgotten. What we're looking at in terms of sharing is that we're going to look at electronegativity. So here we see equal sharing and unequal sharing, and that should really relate between the question and the answer. This is highlighting nonpolar as our answer, but I do want to look at the bottom 2. Electronegativity difference is 0, which means your sharing is equal. Both atoms pull equally on your shared electrons, and then again, your magic word there is nonpolar. So that will point you to choice 2. As it shows in the images, if there is a difference in electronegativity, the two atoms don't pull with the same strength, and you end up with an unequal sharing, which would be a polar bond. And then if it's really big difference, you'll actually get the electrons transferred, and that's your ionic bonding. A simple way to remember is to barf. When bonds are broken, energy is absorbed, and when energy is released, bonds form. This is something that people do confuse from time to time, and as you can see, like this is here, I don't know if you've looked at other tests, this will show up again and again. So we're talking about when a molecule of iodine, when they give you the formula I2, forms two separate atoms of iodine. So we're going from one particle where they're stuck together to two things where they're now separate, and this would satisfy the first half of our acronym. So we're looking for broken and absorbed, which is choice 3. For question 12, we're talking about the degree of polarity. So to take a look at the images we saw, I want to say 2 or 3 questions ago, again, we're looking at sharing, and it says molecule, but it says between atoms, and it says difference. So I don't know which of these words are going to best point you towards your answer, but if we're talking about degree of polarity, again, the word polar is showing up all over these images. So we're talking about covalent bonds. Covalent bonds also, you can be steered in that direction because we're talking about hydrogen and oxygen, which are both nonmetals. And as you can see, the other word that is here with the sharing is this word here, electronegativity. The sharing of the electrons is determined by electronegativity and the difference between the atoms. Electronegativity being a number that quantifies the strength of pull on electrons in a shared pair. That is 2, the answer to the question here. Question 13, this is another one that I feel like we're seeing a similar angle, but a slightly different question. A couple ago, we found the compound out of the group, and now we're looking for the element. Substance that cannot be broken down by a chemical change, that translates to element, and elements can be found on either the periodic table or table S. So this is table S. I scanned down to see which of these showed up. This is krypton right here, so our answer is krypton. The other compound names you should be slightly familiar with, water, of course, and ammonia. And if you're less familiar with organic chemistry, I can write that formula as well. But as you can see, for each of these, there are multiple elements because there's multiple capital letters, and then for krypton, there's just Kr. For question 14, what we're looking at here to help us figure out our answer, the formulas are less important than what's in the parentheses, and what goes in the parentheses is the phase of matter. When you see an S, a G, or an L, these are your standard phases that you're familiar with of solid, liquid, and gas. This AQ stands for aqueous, which means dissolved in water. When that happens, that means water is present as well. So it's compound and water, and whenever you use the and in describing what's present in your sample, that is your code for mixture. Mixture being 2 or more substances that got combined, but there's no chemical change in the combining. These things, they come into contact, but there's no new substance formed when that contact happens. So we call that a mixture, and so the answer to this question is 3. Anytime, that's their way of sneaking in like aqueous and mixture and solution, that's the connection between the words. And then to round off this section, question 15 asks about concentration and which term is used. So for expressing the concentration of a solution, they're asking about units. That's found on table D on the front cover of your reference table. I included the important information right above my head. We're looking at concentration, so I copied over the 2 here, and you can see there you go, it says parts per million or molarity. So we're not looking at any of the other choices because they're not representing concentration on table D, and the answer to your question is 1. Thanks for watching.